till, that's okay. I'll just show the video first. So class is not. I'll just show the, this. So this video shows like Purdue campus a little bit. Okay, not all, a little bit. So it's a little old video. Okay.
When we talk about our best moments, they include humanity's first steps on the moon, alongside stories about the steps we're taking right now at one of our country's greatest institutions, Purdue University. Beauty, highlighted by brick, its fountains and traditions. The campus that stretches across 2,500 acres, nestled in the heart of America. You can feel it in the hearts of the people here. Hardworking, welcoming, and guided by integrity. A family of students and professors who are in this together, all taking the next step, one foot in front of the other. The kinds of innovations that will help solve the world's greatest problems. Persistently pursuing, relentlessly thinking. The next game changers, difference makers, ceiling breakers, innovators, boiler makers. Never stop. Keep going, because there's so much to uncover. And we keep going because discovery is in our DNA. We keep going because it's just as much about the journey as it is about the win. This isn't just a home. This is a launch pad. A community that will propel you on your course, out into your limitless future, filled with promise and purpose and all the tools and resources for your personal mission, encumbered by nothing. Empowered by everything, we are removing barriers and raising expectations. Stand up, boiler makers, each and every one. With more than 630,000 alumni who have your back for life. 2 words say it all. Boiler up. Our greatest adventures are yet to come, and they include you and everything we will experience together when you take your next giant leap.
Just a old video about Purdue. So as you could have seen, in sports is big. Any U.S. American university, sports is big integral part of college life. Now, or it's called American. It's called football in US. It's American football. Purdue is not doing very well this year, so they fired the coach this year. But Purdue is one good basketball team. So we were ranked number 1 in the country last year. For some part of time, we were in the national final championship game. We lost in the final. So, but sports very integral, but again, academics always, so you would have seen Neil Armstrong's, words and Neil Armstrong, statue, and there is another statue that came in between. He was John Purdue. So this also, again, a government, what we call here as government institute. There, the U.S. government doesn't give all the money for universities, but a little bit. So John Purdue gave land when this university started in 1869. That's why the name is Purdue. All other universities you'll see as like with state, like University of California or like Illinois, etc. But except Purdue, since he gave land, it's his name. That's his condition. Okay. And almost, all universities will have, color, their own color. Like our Purdue's color is black and old gold, okay. And we do have, the last frame in that video is a mascot for Purdue. It's called Purdue Pete, and Purdue is called boiler makers. Boiler, making boilers, but the name came for other reasons, but every universities will have a name, they will have their own mascot, they will have own symbol, color, etc. Okay. It's kind of warning. That's what one of the sentence says in alumni. Alumni network is very strong. Usually they have a strong alumni network. Alumni contributes a lot financially, and all they sponsor a lot for campus benefits. So just one video, but there are tons of videos of Purdue you can Google. So anyway, you would have seen aeronautical is big thing, one of the top program. In ABE, Ag and Biological Engineering was ranked number 1 for close to 11-12 years, but we lost the ranking for undergraduate program, lost the ranking this year. But still for graduate programs, we are ranked number 1. Similarly, almost all engineering programs are ranked in top 10, almost all, except maybe 1 or 2, biomedical, environmental, and chemical engineering are not ranked in top 10, but all other engineering programs are top 10 within, even top 5 programs, along with Stanford, MIT, and, Georgia Tech, maybe Berkeley and Caltech. So if you are interested, apply, okay? It will be a good program. You will learn lots of things, okay? So again, as I studied from there, I can see the difference. I studied from here, India and US, right? So the culture will be a little different. So, how you learn will be a little different. So there will be lots of opportunities to grow personally and professionally. There will be tons of opportunities. Okay, so let's move on. Particle size. Any questions? So what was the distribution of food that you ate today? So what did you eat? What did most of you eat? Nothing? What did you eat? Rice? Noodles? Okay. So how do you characterize particle size of noodles? Cylindrical shape, exactly, yeah. So but quantifying shape, size is difficult, right? It's long, right? So what else? You all ate noodles? No. What else did you eat? What's that? Rice. Particle size of sambar? Yeah, it will be very big distribution, right? Vegetables will be larger in size, right? Dal will be medium, and then you might have some suspended particles, right? Broken particles that are suspended in sambar, right? Okay, so we'll go through some of the measurement techniques. So first one, we'll talk about microscopy methods. Okay, so as we talked about, many of you would have used or seen using microscopy for measuring particle size, right? So I'll quickly go through them again. In general, if you can use any particle measurement or characterization method, but you can use any method, but still you want to use microscopy to view the particles, at least some of them, so that you will know. For example, it's a wheat flour, okay? It's about 90 micron size, but when you look, like through our eyes, it looks very spherical and uniform, right? But when you put under a microscope, you can see how irregular the size and shape is, right? So when you put under these particles, any particles under microscope, you will actually see their shape and size and difference in surface texture, etc. Okay, that will give you more understanding about the particles that you are dealing with. Okay, it can be anything. Okay, so common microscopy techniques, optical one, any regular microscopes, right? So usually their field of view is very limited, so we use them for larger particles, right? So we cannot zoom a lot, right? Some confocal, if you are using confocal microscopy, maybe you can get some 3-dimensional images, but mostly we use for larger particles. Okay, so larger particles, either it can be static or moving, means you take a slide, glass slide, spray some particles on the top of glass slide, and then we put them under the microscope, and then there are tons of softwares that you can use to measure the size and shape, right? You all would have used ImageJ, right? Some of you at least. Particles like image processing software. ImageJ, and ImageJ is very free to download software that you can use for characterizing. Okay. But if the particle sizes are small, you can use scanning electron microscope or transmission electron microscope. So transmission electron still for very nano particle, very close to nano size ranges. Okay. Scanning electron microscope is common for again smaller particles which we cannot see using optical microscopes, okay, or smaller particles. Okay. But the challenge of using SEM and TEM, right? So you will have to do lots of sample preparation. Okay. It's not direct and easy like an optical microscope. So you'll have to use some gold-plated particles, spray them, and then equipments are also very expensive to use, etc. Right? But they still can give lots of good understanding on the particles. And again, they have higher field of view, right? So you can measure up to nano size ranges, right? Okay. So microscopy again, in general for normal optical microscopy, you can see for larger particles, sea sand, or large any type of granules, even wheat flour, etc. But if you go down to smaller particles like pigments, paints, pigments, smoke particles, viruses, etc., then those are like submicron, right? Then you'll have to use SEM or transmission electron microscope. Okay. Any questions? Any of you use microscopes for measuring particle size? No? Okay. So again, you can get the shape and size from the same measurements. Okay. So one of the major disadvantage of using optical microscope, it's from two-dimensional projection, right? So how are we characterizing is from the two-dimension, from the field of view, right? How we see the particle, right? So if the field of the projection changes, the particle size will also change, right? So for example, if I am seeing this as from the top like this, the size is different. But if I am seeing like this from the top, the size is different, right? So the particle orientation or the projection will highly influence how we characterize the particles, okay? So that's one big, disadvantage of using microscopes. Again, lots of sample preparation is needed. Size distribution, as we just talked about, before lunch, it gives by number. So if you're using lots of a number of particles, then your distribution might be different than a smaller group of particles. Okay. And again, yeah, preparing particles will also be a little challenging when we prepare for measurements. Okay. So what are some of the microscopy, you would have, at least ag engineering students would have learned about some size measures that we calculate from microscopy technique, right? Anyone? Any? What are some of the size measures that we calculate for particles? Obviously one is size, right? What other, characteristics that we calculate? Shape, okay. What is it? Diameter, okay. So what are the shape parameters that we calculate? Okay, exactly. That's what I was looking for. Sphericity, circularity, etc., right? So from the projections, right? So common, size measures that we use again or calculate from the microscopy technique. Okay, one is again that circumscribes the particle. Okay, you draw a circle around the particle, and based on that diameter, you calculate the size. Okay, the other is minimum chord diameter. Again, that's within the particle, internal projection. Okay, the smallest circle that fits within the particle, and then you calculate the size based on that circle. Okay. Other things, you would have learned about Ferret's diameter, Martin's diameter, etc. Right? Ferret's diameter, again, the projection, external projection of the particle, again, with the change in orientation, the size will also change, right? So it's not unique. So you can have more than 10 values, for one same particle, same, for Ferret's diameter and Martin's diameter. Okay? Ferret's diameter, again, based on the projection, and Martin's diameter is from the projected area. So the line or chord that dissects the particle into two equal areas. Okay, so that's the Martin's diameter. Okay, again, same thing, like Ferret's diameter, Martin's diameter is also not unique. Based on the projection, this value can also change. Okay, so how do we use these values? Okay, one more thing. So that unrolled diameter, again, unrolled diameter to get accurate size based on the projections and shape variations. Okay, so you get the diameter or the radius of the particle across 360 degrees, and then you calculate the overall radius from when you unroll a particle. Okay, so it gives an accurate mapping of the particle based on the irregularities or the surface irregularities. Okay, one of the challenge will be, if you have overlay particles, two projections, then you might get two values, right? So then you get wrong values. So you may not be able to use that if you have overlay projections. Okay. Okay, so we use these projections to get different values like equivalent circle perimeter diameter, equivalent circle area diameter, volume diameter, surface area diameter, etc. Right? You all know these equations, right? So the area for a circle, you calculate from the diameter, same area projection from the diameter, right? Volume from the spherical particle, right? Volume and surface area, and then area to volume diameter, right? You all know these equations, right? You remember at least, or if you don't, make sure you remember, okay? Because we will be doing some calculations now, okay? So okay, calculate these. So for the cylinder particle, it's not a noodle, okay? It's a small particle, okay? Small cylinder, 10 mm by 50 mm size. The equivalent circle area diameter, okay, equivalent sphere volume diameter, equivalent sphere surface area diameter, and the specific surface diameter. You all remember the equation, or do you want me to go back to that slide? Area diameter. Still I show that equations. I know we have 4 BS agriculture students. You may not study all these things, size and shape. Do you? No. What's that? Any question? No. If you're bored, you can also do the calculation. What? What? Yeah. See, you know the formula, you can calculate. Okay, so anyone got an answer for the first one? Okay, I'm not for the value though, but what I got was 25.24. Okay, and make sure, assuming the cylinder lies on its cylindrical side, so this is the projection that you are getting, 10 by 50. Okay. So for equivalent circle area diameter, okay, so you can get the projected area, right? So you know the projected area of the cylinder. So what you are calculating is dA, right? So you calculate dA, okay. So that will be the equivalent circle area diameter. Okay. Okay. So anyone got the value for sphere volume diameter? Next one. Did you? How much? 19, exactly 19.57. So anyone for the third sphere surface area diameter? Do you get? 23.45. The last one? So again, the formula, yeah, my sphere surface area to volume diameter again, left. What's that? 13.64. Again, these are, this is how you calculate if you're using, automated image analysis softwares like ImageJ and etc. Okay, so based on from the projection, you calculate those diameters. Okay. So again, particle shape factors, as we talked about, the orientation changes the particle size, and also, the shape will also affect the particle size, right? This is microscopy technique, right? At least for microscopy technique. Okay. So there are, shape factors. I will not, go much detail into it. Shape factors that you can use to convert or calculate these, particle sizes from the volume, from the surface area, or from surface to volume ratio too. Okay. This gives a little bit close approximation to the change in orientation or change in shape when you calculate the particle size. But when you use shape factors, usually you increase the error in characterizing. Okay. So the error also increases along with the use of different shape factors. But again, we'll talk about shape factors a little bit more when we talk, when we go into particle size distribution. Okay. I'll skip this one again, this shape factor. So microscopy, when you use any microscopy analysis or software, this is again from Malvern, G3ID that uses optical or slides to get the particle characteristics. You get almost all the size and shape values like, convexity, circularity, perimeter, length, width, circle equivalent. So CE here means circle equivalent diameter. So it's two-dimensional projection, right? So it's taking the particle as a circle, okay? Not volume, not a sphere, it's a circle. Okay. So from that circle, any shape material, again you get the CE diameter. Okay. So you can see from this, if the aspect ratio is high, then the values that you get is very wrong here, right? Because this is not even close to a circle, it's high aspect ratio particles. Okay. So if the particles are very close to circle or spherical, then microscopy will give a good result, but not for high aspect ratio particles, not for noodles. Okay. We still can, calculate, particle sizes, but it may not be very accurate or, very close to the size that we see. Okay. Any questions? So there are, again, for microscopy too, there are tons of standards. If you Google, British standards, ASTM, ISO, etc., that you can use for character that gives, these standards gives different, size measures based on two-dimensional projection. Okay. Okay. Move on to light diffraction. Okay. So light diffraction is simple, right? Simple technique, you would have, many of you would have used Malvern or any kind of, laser diffraction measurement, right? How many of you used a laser particle size analyzer? No one? You have? You should have one here, right? In food engineering?
It's there, but it's not working properly.
Oh, okay. Okay. Is that a Malvern? Yeah, okay. Okay. So again, this is a very, simple and easy, simple to measure and easy technique. Okay. If you would have used, you will know, it might, you get the particle size in maybe in a minute or two maximum. Okay. So you load the sample and it gets, you get the report. Okay. Very easy, very simple measurement. So it's depending on the technique, or the measurement is based on light diffraction, how much light is diffracted from the surface of the particle. Okay. So again, we can use for a wide range of particle. So compared to microscopy, this method uses or compare the particle to a sphere, a spherical, identical spherical uniform shaped material. Okay. So in microscopy we are using circle, but here we are using a sphere. Okay. So it gives a volume distribution. It compares the volume of the particle to the volume of a spherical, uniform material. Okay. Again, couple of methods, either it can be in suspension in liquid or in air too. Both are common, but most used is the liquid, dispersion systems. You suspend the particles in a liquid, they will be, it will be circulated in the liquid, and then light or laser pass through it, and then from the diffraction you get the, particle size. Okay. So how it works again, usually there will be a chamber through which, the particles are suspended. Okay. So laser or light passes through the, those particles, and then based on the diffraction, smaller particles will have a larger diffraction and larger particles will have a smaller diffraction. So the instrument again collects all the diffracted information, and from the collected information you get the size, shape, volume, etc. Not shape per se, but size, volume, surface area, etc. Okay. So again, it all keeps on summing the data. So one of the major challenges, it's based on diffraction, right? So it's limited by the concentration. So amount of powder that you add or particles that you add in the suspension should be limited so that you can quantify all the diffraction. It's not overloaded within the load cell, within the cell. Okay. So do you guys learn about light theory, etc.? Theory of light, little bit? Ag engineers? No? So you might have learned, heard about these scattering theories, right? So Fraunhofer scattering, me scattering theory, Rayleigh scattering, etc. Right? So different instruments. Why I asked Malvern means different instrument uses different scattering theories. How they collect those diffracted information from those particles. Okay. So mostly you might see in the instruments Fraunhofer and me scattering theory, mostly for particle sizes larger than 2 microns or around close to a micron and submicron particles. Okay. But if it's small, particle diameter much lesser than light wavelength, etc., then you use different scattering techniques or scattering theory. Okay. And there are tons of theoretical literature on these scattering theories, and then useful how they are used for particle size measurements. Okay. So again, most of it's Fraunhofer and me scattering thing. Okay. So as I said, rapid analysis, very quick method of measurement. So within a minute or two, you get the particle size, surface area, etc. But it also comes with some challenges, right? So one is the limit of suspended amount of particle that you can have in suspension. Okay. The second is we should know the optical properties of the material. Okay. So that's a baseline that you wanted to, know. So the instrument, when you measure, it will ask for the optical property of the material. Right? But if you are buying a instrument such as Malvern, usually for all common powder particles, they will have the optical property listed there. So you don't have to go and measure it, but you just choose the appropriate optical property. One other major disadvantage, again, it assumes spherical particle, right? So if the particles are of high aspect ratio, then the error in measurement will be very high. Okay? If you are measuring for noodles, the error will be high. But if you are measuring for like tennis balls, then again, we may not measure for tennis balls, but they're very close to sphere, right? Then the error will be very small. Okay? So if it's close to spherical, less error, but if high aspect ratio, then the error percentage will also go up. Okay? Again, optical properties, again, how it corresponds to the the measurement is very important. Again, I think it's simple measurement. If you have a refractometer, you can measure the optical property, but if not, most of the instruments will have the optical property listed in there itself. Okay. So this is an example report from Malvern master size. So you can see, you'll get the specific surface area other than the size, surface weighted mean diameter, volume weighted mean diameter, etc. Okay. So D3243, etc. I think we'll talk about those numbers, in the next particle size distribution when we talk about, distribution. Okay. So other than size, we get some surface area related measurements too. Okay. So and again, it gives a very nice plot of volume distribution. Okay, particle size and how much percent volume of that particles are within that mix of powder that you are measuring for. Okay. Any questions? How many of you are feeling sleepy already? Was the lunch good? Okay. Okay or good? Okay, good. Okay, so the next one, focus beam reflectance measurement. Again, very similar, using laser. Okay. If you worked in a dairy industry, not milk, but dairy industry mostly. So this is very commonly used in by the dairy industry. So if you are processing milk into different products, like preparing, making yogurt, okay, or other products. So you'll want to see the protein fragments in those, right? So proteins are usually, high aspect ratio particles, right? So for continuous formation of or continuous measurement of protein suspension in those milk products, they commonly use this focus beam reflectance. So as I said, mainly for high aspect ratio particles, since it measures the chord length. Okay, so it measures the chord length of the particle. Okay, so by again passing, passing laser beam through those particles, and again from the duration of reflection from those particles, you get the chord length of the particle that's suspended within that, any medium. So why I said, dairy is very common user of this FBRM, technology for making different products. Okay. Mostly for, process situations, so you don't use it for, particle size measurement per se, but to monitor the process changes. Okay. So I said, how much protein particles are forming within, or how much it's suspended within that medium, that you are manufacturing, etc. So mostly for online monitoring, and then again measuring the chord length. Said, for mostly for high aspect ratio materials. Okay. Any questions?
How much sample will be required for
this? This is again for online. So if your process depends on process, you don't need a lot. So if it's a small batch process, you can still use some.
It's not in a milliliter.
Yeah, it will be mostly for process, like liters. Yeah. Any questions?
So it is suitable for only liquid food or solid food?
Mostly suspended solids. Yeah. So, so if it's pure solid, they don't use it. It's mostly for suspended. Like I said, dairy is very common example. Or, crystallization. So in pharmaceutical industry, you might know, right? So those medicines are formed by crystallization technique, right? Crystallization. So how the crystals are forming during that process, they use this, FBRM is common, okay? Because crystals, again, high aspect ratio, right? Usually they are not spherical. So the other common, again, light extinction common method is how much light passes through the particles, okay? So based on the light that passes through the suspended particles, you can get their size, okay? Again, there are different theory associated with it. Again, how much, in general, it's how much light passes through the cloud, okay? So if there are smaller particle, again the diffraction will be larger particle less diffraction. Again, if it's suspended thick as a cloud, then the extinction will be high. That means the light doesn't pass through it. But again, it's not not used for most not used for large particles, but very common for smaller particles, okay? Again, based on how much light passes through the cloud, okay? So said samples must be very similar to the laser diffraction or light diffraction theory. It should be in dilute suspension. If not, you will be doing like overcrowded particles with but you will not be able to map all the particles suspended within that medium, right, within that cell. Okay, the dynamic light scattering, you might have maybe seen this, this common again, mostly for submicron, very small particles which have lots of Brownian motions. Okay, larger particle you may not see Brownian motion, right? So they just suspend and then they settle down, right? But if the particles are very small, they will be moving around a lot, right? Like dust particles in air that's suspended, they will have lots of Brownian motion, right? So for those type of particles, this is common technique, dynamic light scattering. Again, very similar principle, pass lights, pass through the cloud, and based on the reflection, then you calculate the size of those particles, okay? Mostly for very small, close to nano size ranges, okay? So 3 nanometers up to about 6 microns, which we see commonly in this range, where you see a lot of Brownian motion of those particles. Okay. And polarization intensity differential scattering. So many of the light measurement techniques is limited by the size of the particle, right? So this Spitz technique uses different wavelengths, so you can capture different sizes of particles within the same instrument, okay? So if you have a mix of very close to nanomicron, nano size particles, and some mix of micron size particles, then the other instruments may not be able to accurately quantify, but Spitz can quantify this highly distributed particle size mix, from small to large. Since you, as you can see, they will use different scattering angles, okay, from larger scattering angle to smaller scattering angle, so that you can capture any different sizes within that mix. Okay, it's not very common, but this technique is also available out there. Okay. And there are many different standards, ASTM, British, ISO, etc., that defines these standards of particle size measurement using light, reflection, refraction, absorption, etc. Okay. Okay, any questions? Any questions? No questions? So we'll talk about sieving, okay? Sieving is a common technique, right? So how do we use sieving? So you take a stack of sieves, right? So how do you decide which sieve to use? What is that? Someone said something.
According to mesh size.
Mesh size, okay. So you follow some standards, right? So depending on the sieve opening, right? Okay, so again, a sieve usually, a pan with openings, and again, you might see different, sieve openings based on the size or distribution of particles that you wanted to measure. This is the least expensive method, right? When compared to microscopy or laser diffraction, etc., you just need a set of sieves and some shaking mechanism, right? You shake for some time, and then you get the particle size based on the amount of samples collected in each sieve, right? So very easy method, and very simple method too. So there are, when you take sieves, there are different types of sieves. Some of you, if you have used sieving techniques, you might have noticed, right? So if you change the standard of the sieve sizes, then the openings may not be the same. Okay? So it depends on how the sieve meshes are formed. Okay? So if it's electroformed, it's more uniform and close than a woven wire sieve. Okay? If it's woven, then the size may not be accurate. It's more than rectangle than a square. Instead of an electroformed sieve. So electroformed is mostly precise than the woven wire and the perforated ones, but in general it's little expensive. Most commonly used for smaller particle size sieves. Use those electroformed sieves, but very commonly for large particles we either use perforated or woven wire. Okay, so again, will be high tolerances. Again, 10% or 5 to 10% variation is also there due to this difference in opening. Okay, one is opening, difference in opening. The other is how the particle fall through the openings. Okay, if the orientation changes, then the size might also change. Okay, and mostly we measure the chord diameter. Okay, so depending on the orientation of the particle, so what we are measuring when it passes through the sieve is the chord length. Okay, of that particle. Okay, so again, minimum, the maximum, chord length that fits within that square opening will allow the particle to fall through. Okay. Again, we calculate the arithmetic mean diameter again based on the amount of sample collected in each sieve, right? Any of you use sieving calculations, like particle size from sieving? No. Any of you used? You have, right? So which standard do you use? Anyone remember? Taylor series. Okay. How do you calculate the particle size or the arithmetic mean diameter? Anyone have used? At least ag engineers. You may have used ASAB standard, right? You might remember? No? So from your undergrad labs, when you go back and check, you might have used ASAB standard. Okay? But in general, again, that's the arithmetic mean diameter that we use. Okay? But as said, there are two different types of, actually three different types of sieves series, like ISO, ASTM, and Tyler. Tyler and ASTM are common, I believe. ISO maybe, but most sieves that we use, either it should be Tyler or ASTM standard sieves. Okay. Again, successive sieve apertures usually follow a 2 power 0.25 size openings, are mostly for these standards, but except for French standard, it's 10 by 10 the power 1 by 10. Okay. So again, approximate progression is about 2 power 1 by 4. Okay. Okay. So can anyone solve that? It's easy. How do you prove that the successive opening sizes increases or goes in a progression of 2 power 1 by 4? You can do that theoretically. Anyone taking a shot? Anyone trying? You're clear on the question, right? No? What's that? Okay, so can you prove the progression of aperture sizes follow this rule, 2 power 1 by 4? Sure if I have that in the slide, but again, I've shown all those sizes here, and you can get from all the standards to the opening sizes depending on different sizes here. Okay, I have the answer there too. I don't want to show the answer. Okay. Anyone want to try?
Okay, so for if you take that 25 and
You don't have to use any values theoretically. So how does it, how does the particle falls through? Maybe it's much, maybe I'll show the answer. Okay. So just showing how it changes by 2 power 1 by 2. Okay. So if you're assuming the particle sizes, and if you know the if one major assumption that we make is the shape doesn't change. Okay. But in general that's not true. In general the shapes may not be common or same for the particles that are passing through different opening sizes. Okay. So again, from the surface characteristic, surface from the shape factor, and you don't have to use the shape factor, but assuming shape factor is constant, you can know that particles or the sieve sizes use the formula of 2 power 1. Okay. What is any question? Okay, so typically, so if we talked about using arithmetic, mean diameter, right? In general, again, we are using the weight of material to get the size, right? So many people, many times we don't use that arithmetic mean diameter, but the normal common, convention is using a positive negative sign, right? So a plus 40 minus negative means the sieves, for example, plus number 4 plus, minus number 4 plus number 40 means, more than 90% of the powder will pass through number 4, but again then retain that number 40 sieve. Okay. That's a common convention. So that gives a distribution. Okay, it passes through this opening, but it retains at this sieve. Okay, so the size of the particle will be within this range. Okay, so that's a common again convention. Again, or percent of material that's retained on each sieves. You get a distribution. Okay, so you get the amount of sample retained on each sieve, and then calculate the distribution of the particles. Based on size. Okay. So I'll not go through a lot. So most of you would have used sieving technique, right? So common vibration method, but if the particle sizes are small, then you could use air jet sieving or supply, use some additional air, okay, so that it flows through the openings very easily. If you fluidize them, it flows easily. If it's little cohesive or agglomerate, if the powders have little agglomerating tendency, you might want to add some flow aids or some dispersants like stearic acid, fume silica, etc., that makes the particle to flow easily through the sieve openings. Okay. If not, kind of clog. Okay. Wet sieving is also common, again, if they doesn't dissolve in liquid or water, but you can use other alcohol medium or alcohol solution too. But that gives little better accuracy for cohesive powders. When you're using in a liquid medium, you avoid formation of agglomerates, small agglomerates. So it gives the measure of individual particles when it flows through the sieve, okay, rather than large agglomerates. Okay. But if you have a larger size distribution, and if you wanted to use sieving method, so one of the suggestion that we provide is first separate them into two small two lots. one large particle group and one small particle group, and then measure them separately, okay, instead of having to use a large array of sieves, okay, large number of sieves. Again, how much time we use for, how much time we have to sieve. Again, there are, different equations that we can use to calculate the amount of time that's needed. But most of the powders, if you check any standards, they would have provided the minimum amount of time that you have to sieve any powders, right? It's usually about, close to 10 to 15 minutes, anywhere from 10 to 15 minutes of sieving. But if you do not know the time, ASTM standard suggests you sieve them or vibrate them till there is no more than 0.5% difference in the sieve samples or the sample weight. Okay. Again, so usually by distribution by mass, and again, in general, you have to monitor for the weight change, during the sieving process. Okay. And this is a simple method, almost you all would have used, right? So most commonly we get the distribution, either cumulative distribution or the frequency distribution, to get more in-depth analysis of the particles, right? So you can get D10, D50, D90, or 90 particle size. You can get the span. You can get other meaningful information from this distribution too, right? Most of the distributions or any distributions, but based on the amount of samples, you can get the distribution. So I'll skip this. And for ag engineering, we commonly use this ASAB standard for using sieving for different particle sizes, but there are tons of other standards. ASTM, if you're using flour or food related material, ASCC, American Association of Cereal Chemists, also have a standard for sieving of food powders. Okay. We'll quickly go through this. I do have another online meeting at 4 p.m. So hopefully, and then I think Dr. Gotke will be teaching the next class. Right. So we'll quickly go through the fluid-based measurements. So you would have known about Stokes diameter and aerodynamic diameter, right? Stokes diameter again uses the principle of Stokes law. Okay, so if your particle is suspended in fluid medium, okay, in general, the force from the weight goes downwards, and then the drag force and the buoyancy force tries to balance that if the particle needs to be suspended in that fluid medium, right? So all those equations, drag force, weight, inertia, and also buoyancy force. So you equate them and you get the particle size, provided you know all the viscosity, all the other important stuff, viscosity, density of particle and the fluid, etc., and then you can calculate the Stokes diameter. Okay. Again, there are instruments that we'll talk about that in a minute. So one other major assumption here is we are assuming this as a spherical particle, right? That's one of the basic assumptions that we use in Stokes law, right? The particles are spherical, right? So again, for high aspect ratio, the values might be little different or little error, when you use Stokes principle. Right? So sedimentometers, I'm not sure if any of you used, it's very common that uses Stokes principle. Like you suspend the particle and then measure the amount of time or monitor the amount of time that it takes to travel from some distance within that sedimentometer or from top to bottom. Okay, so from based on the time and the distance, you can get the terminal velocity, and if you know the terminal velocity, you can use that Stokes law to get the diameter. Okay. So advanced sedimentometers uses X-ray again to get more accurate determination of their height and time when it passes through the fluid medium. Okay. So major advantage, we can go up to about 50 nanometer size particles using this technique to get the particle size. Okay. So some of the important things that you have to keep in mind. So the difference in particle density between the particle and the fluid should be high enough so that you see the difference when the particles are settling or moving through the fluid medium. Okay, so if they are very close, you might not see the difference at all. And again, if the particles are different in density, then you might get error in results. So almost all the particles that you are using in the lot should have very similar identical density values. Okay, if not, that will be little errorful. Again, temperature will be the major important, and again, dispersing liquid, deagglomeration, etc. Careful consideration that you have to keep in mind when using this liquid method or Stokes principle. Okay. Same like other methods, very simple and easy measurement. Aerodynamic diameter, very similar principle. Only thing, we are not using any liquid, but using air to suspend. Okay, so similar depending on the force equilibrium. Okay, you can, again same, using the Stokes principle. If you know the aerodynamic drag, if you know the weight of the particle, the buoyancy force, you use them and calculate the diameter. Okay, so again, same settling velocity. Again, same spherical particle assumption is valid here too. Okay. Okay. Can anyone give an example of why do we apply this aerodynamic diameter? It might be a little long reach, but any example?
Effect of force from all sides, like it has some tension.
Which one can? Tension. Tension, yeah, no, may not be.
How much force required to lift the particle?
You can. What's that? Air classification very close, yeah. But you can, what's that? Cyclone separators, yeah. Cyclone separators are very closer. Okay, how much air will interact with the particles, right? So cyclone separators, except not pneumatic handling, but cyclone separators, little bit of air jet sieving, etc. But that's air classifier will overlap in both sieving and also in this aerodynamic principle. Okay, but cyclone separators might be very common. Okay, but we don't use this technique much in food. Okay, very commonly used by the pharma industry. Okay, any of you use inhalers? Inhaler, right? Sometimes any kind of inhaler. It could be medicine or aerosols, etc. So that's very common application of aerodynamic diameter. Okay, when you are using inhaler, how much amount those, if you are using medical inhalators, inhalation systems, how much time it takes for the particle to settle in your lungs, how much time it takes to reach, to the lungs. That's very common example. So they use a specific instrument for this. It's called the inertial factor. For finding the aerodynamic diameter. As I said, it's for very small, close to nano-sized particle range. Okay. Again, when the particles pass through this, it suspends and settles into different columns, within that instrument, and then based on how long it passes through that will decide its diameter. Again, very commonly used in pharma and mostly inhaler suspended particle manufacturers. Electrosensing, another common number based approach, again based on counting the number of particles, but it can also give a volume based distribution. So this is also a very common instrument. You might have seen one, or you may have one here. It's called the Coulter method. So simple measurement, so the particles are suspended in fluid medium, and when it passes through the electrodes, with the change in voltage, its particle size is calculated. Okay, so the change in voltage corresponds directly to the size of the particle. Okay, so again, that's again simple measurement, used for, again, assumption of spherical particle is valid here, 0.6 to 800 size. Okay, and it's also, again, it's not very common as laser diffraction, but it's also this Coulter counter is also a common instrument that you might see in many places. Okay. And again, some standards, ASTM, ISO. So coming to almost close to the particle size lecture. So the common size measure, particle size, is the almost the most important property that we measure for any particle materials. Okay, so it influences all our design, handling, whatever calculations we are going to make will be influenced by this particle size. Okay, we can use any different techniques, but the suggestion would be at least put some of them under microscope and see how they look like, at closer, it gives more information about, the particles itself. Most common, again, as we talked about, laser diffraction and sieving. Mostly if you go for industry, most common is, the laser diffraction. It's very quick and easy. Almost all industry will use this, laser diffraction technique. Okay. Again, comparing two different techniques is not suggested and advised, as we talked about. We use different physical principles, so you don't have this. You're not comparing the same sizes, from different measurements.
Hello, check.
So
Hello, check.
check this text. It's not a textbook, book by Allen on particle size measurement. You have lots of theory behind all these, particle size measurements in that textbook. It's not, it's not a textbook, it's a book. Any questions?
So
51. This one?
what does it mean by 0.5% mass difference? You told that the time should be up to 0.5% mass difference. I didn't get that.
So this one, right? This line, right? So many of the standards will have specific time, right? For example, if you are measuring for wheat flour, you will have to sieve for, I think, 12 minutes. Okay. But if you do not know the time, how much time will you sieve the sample or run the vibration system? So the common, suggested by the standard is you sieve until there is less than 0.5% mass difference between two sieves.
Between two
Sieves, yeah. So, for example, if you have one sieve, 20 micron sieve on the top, 10 micron sieve on the bottom. Okay. So if after you sieve for some time and check the weight of both 20 micron and 10 micron, if there is some change in weight, you still continue sieving.
Mainly the overflow that is staying over the screen.
Yeah, over there,
Okay.
yeah.
Over these two successive
Yeah, over the
states.
successive sieves, yeah. So,
That difference should be 0.5%.
yeah, less
between
than
these two.
0.5%, yeah.
Okay. Okay, sir. Thank you.
Any other questions? Yeah, go ahead.
Sir, my question is general, like if we want to do a milling and we need to optimize it, so how can we approach this, like by particle size distribution?
Okay.
Like we need a particular size range, let's say 40 micron. So how should we optimize that milling process?
So, you'll have to do lots of things. So, for example, if you wanted to optimize the milling, so in the current industry setup, how do? They do, calculate the particle size in between during the process. Okay. So during milling, they calculate, or they take subsamples and then calculate the sizes. Okay. In general, there, at least in wheat milling, since you said wheat milling, technology is very advanced. They have perfect sieves, sieving mechanisms, air purifiers, etc. That gives very close approximation of the or close particle size ranges, right? So only thing is you take sample and measure the sizes and then adjust your process till you get that size.
Okay.
Right.
Sir, if we have this lab scale equipment like ball mill and hammer mill, in that we can do that.
Yeah. So large process or small process, you can still do that.
And which method will be suitable, sir? Like laser one or the sieving one?
So again, depend on your process. So if you are interested in more spherical related thing, then use laser. But if you are, just wanted to see the process change, the process difference, then sieving will be easy and convenient. Okay. Sieving will be easy and convenient.
Yeah.
But if you wanted more accurate, then laser diffraction will be better. Yeah. But if you have money, you can have an online system too that quantifies the particle size continuously. So you install a laser system. Okay, inside that whatever milling system, milling unit, and then you continuously characterize. I'm not sure. Have you heard of an industry called Bueller?
Yes.
Bueller, Bueller manufactures lots of process machines, right? They do have an inline or whatever online, particle size measurement system, mainly for milling and grain processing industry. When the flour comes out, it gives the automated, particle size. So,
Thank you, sir.
yeah, no problem. Any other questions? No questions? I see that you are relieved that I am stopped my lecture, right? More satisfied faces. No, I'm just joking, but well, we'll talk about particle size distribution tomorrow, right? Tomorrow, what time? It's 9. Okay. Okay, so any other questions? But come up with more questions tomorrow, okay? Think about it. You don't have to sit and think while walking. If you come up with some questions, we can discuss more, okay? Today, Dr. Godke will be teaching. So, can you pull that out, my child? Yeah. Thank you. I was waiting for you to ask all the questions. You missed it.
There is a tea break of 10 minutes.
Yeah.
Everything is good.
Yeah, no. Don't you hear? Still waiting for my meeting, right? No, you can do it tomorrow. But I'll be here. Not going. I'll just email them for the.
video is not playing in the full screen in the slide. Is there a way?
Okay, can I be in the room? You can come, no, there, in
There.
this room.
Guest house.
Yeah.
Yeah.
So can you give me a call when you're done? I'll be there.
Okay.
Okay.
Can you go?
Someone can drop me there because it's holding.
I'll ask my.
Okay. Are you okay learning something? Okay. अच्छा, पंजाब का है। Yeah, that's okay.
लगा लीजिए
ज़्यादा क्लोज चाहिए या ठीक है ले लेगा हेलो हेलो एम आई ऑडिबल फाइन आवाज़ आ रहा है लाइव स्ट्रीम में हम टी ब्रेक अगर होता है तो टी ब्रेक डिस्प्ले करते हैं क्या नहीं अब नहीं अब ये बस लास्ट क्लास है ये 5 बजे हमें बंद करना ही पड़ेगा ठीक है बाकी कुछ बाहर है क्या someone is outside you can call them someone is outside you can call them Okay. Good evening all. So in this lecture I will be taking on DEM modeling and simulation of particle flow. I am Dr. Bhupendram Ghodki, Assistant Professor Grade 1 in Agricultural and Food Engineering Department. Right. So what do you understand by this DEM, the term DEM? Do you have ever heard of it? Okay, right, discrete element method. So there are different numerical modeling approaches for in the case of food process, say any process you need to model, say a fruit juice is there. So a juice is basically a, you can say a liquid, right? So it is a continuum matter, right, like water. So and some particles are there, say you are filling the grains in the silo. So they are discrete particles are there in the grains when you put on the grains from the say a hopper, right? So based on that also we can say there are two approaches, right? The first one is continuum approach, right? It is, we can see a continuous matter is there on the right side, a flow of fluid is there in the channel, right? So this space, it is based on the continuum mechanics, and you can divide this in the form of the grids, right? Since these are the continuous matter, right? And on the each grid point you can solve the partial differential equations, right, PDEs based on some model, right. So but in the case of this discrete we have some discontinuous matter. On the right side of the slide you can see I am pouring a cumin seed from a vessel, right, from top to the bottom of it, right. So you can see there are some particles, right, of the cumin. Those particles can be represented by the individual particles, right, which are represented here as a spherical grain, all right. So this spherical grains they have some interaction properties, all right. So these properties needs to be defined. When you model these single particles, individual particles, we can see a bulk behavior of the particle while simulating or modeling, right. So this is what we do in discrete element method, right. Now what is DEM? In this slide you can see we can define this as a way of simulating discrete matters so that we can see the bulk behavior of the particles. In this we can do both the kind of motions, a rotational one and a translational one, right. Suppose I am hitting a ball which is stationary, what sort of motion do you guess, right? I am hitting a stationary ball with a rotational ball. What are the properties that may interact with the, say, this geometry or with the floor? Friction, correct. Density, true. Poisson's ratio, your coefficient of restitutions, you told most of the things. What do you understand by coefficient of restitution?
It tells the particle elasticity as well as the velocity behavior of particle
Okay.
after and before collision.
Yes, it is the relative velocity of particle after the collision. Say the two balls are colliding, just their relative velocity after the collision, then before the collision, divide by before the collision. Okay, so it gives you that. So it may represent as a loss of kinetic energy in the motion, right? It represents actually. So its value is between 0 to 1. Okay, 1 is perfectly elastic, and 0 is inelastic. Right? So these are some of the properties which we take into picture, right? And here we define the displacement and rotation, like I told. Okay. Now in this slide, this is showing the overview of the DEM, right? Where we can apply it, right? So you can see it is in the automotive industry, pharmaceutical industry, we can apply it over there. While say in a pharmaceutical industry, you need to put on the tablet, making a tablet with the powders, you can apply DEM. In the agriculture, mineral processing, right? And say on the right side, you can see a harvester or a spraying machine is there with the grass over there, right? You can put on a tractor, like which is related to the agriculture, right? The interaction of the tractor tire with the soil, right? Then the spraying of the liquid chemicals on the crop, right? So we need to see the patterns also, right? But this is through continuous matter approach, spraying and all, right? And the sieving process on the very right of the slide, I can see, yeah. This one, okay, it is not connected, okay. So this is the sieving on the right side. It is grain sieving, yeah, just Professor Kingsley was talking about a little earlier, right. So this is showing the types of software which are available in the commercial market as well as in the open source. On the right side, they are the open source softwares, right. On the left side, it is the commercial software. So let us see, it is the EDEM which is there, it is now acquired by Altair Group, right. Rocky DEM is there, Newton's DEM, right, and PFC. These are the commercial codes which are available. Right? On the right, if you want to try your hands on, there are some open source softwares also, like Yade, Lights, ACES Particle, and Mercury DPM. In this slide, you can see DEM modeling in grain fruit handling, an overview and processes, right. So I defined this in two forms, right. Free flowing grains, right. In free flowing, the example is taken as filling and discharge of the silo, and there are n number of researchers who did the work, right. Likewise, in the confined grain, conveying can be done, cleaning and separation is one, all right. Impacting of the grain kernel, or impacting of the fruit during the transport. Say I am transporting an apple, right. So I need to see the impact during the transportation on the apple. Is there any damage on the apple, a bruise damage or so? So that can be done through the DEM, right. Silo probing, compression and shearing, and grinding. So grinding, I did my work, most of the work on it, and in the compression and shearing part, say you are pressing some grain in the universal testing machine, so that can be a compression and compression part, right. Then in the grain drying and the 3D printers, like in the 3D printers, powders are there, it is spread on the bed and so on and so forth. So this process also can be modeled through DEM, or you can simulate that, right? Provided you need the input properties, right? You need to define in the software, right? We will take care of that, right? I will show a slide later on. Here you can see, like I was talking about the apples and all during the transportation on the top right corner, right? In the center you can see on the top there is a compression of, that is a black pepper seed, right? And I saw the force deformation characteristics, right? I prepared a seed with the small balls with some bond properties, right? Then on the left side there is a conveyor, bucket elevator with a flow of grain. On the right again sieving of the wheat grain is there, then conveying on the bottom side of the slide. In the center you can see the grinding, how the particle moves within the grinder, right? And the top left, in the left corner you see the fibers which are moving on a conveyor. So coming to the fundamentals of the DEM, right? So what happens before DEM and now what will happen after the DEM. Before DEM we are solving the equations, there are some empirical equations, thumb of rules are there, and you can see in the top left side of the slide there are vectors, okay? We define the normal force, tangential force, likewise for the velocity, and we find the resultant force, all right? But with the DEM we do the virtual testing, we can change the design or the dimensions of the machine, right? We can put on the grain, right? We can even change the feed rate, and if we are interested in the discharge rate we can do that, right? And of course this reduces the cost, you know. So a little background of this evolved with the molecular dynamics, where transitional part is there, and in 56 and in 79 it was now discrete element method. You can see that the size and the shape of the particle, it can be varied in discrete element method, right? And there is a rotational degree of freedom is also involved, right, in DEM, which is not there in molecular dynamics. So in this slide you can see the particle J on the top, which is hitting particle I, and the breakage of the forces are there, right? Two particles are colliding, right? So the force, you can define that in normal and tangential direction, force acting on particle I due to some particle J which is hitting it, right? Yeah. Oh, you can't see. Oh, no issues. Which is, now you can break this, right, in normal and tangential direction, the forces. Then there are forces due to rotation also, right, torques I can say. So this is governed by Newton's second law of motion, and you can represent it by some contact model, which is on the right. You can see represented by spring and dashpot, and the two elements, two particles are connected with a slider, which is in blue color, okay. So force equal to mass into acceleration on the bottom left first equation, right. This force are broken down into different component of spring and dashpot, and then normal and tangential direction. Likewise the torque, the second equation, torque, you can see moment of inertia and omega v, right. That is rotational velocity and moment of inertia multiplied, right. So this whole cycle, it repeats for a certain time steps, right. So this is the basically the background of it, and this contact model is dependent on the part of the application we are doing. We can develop our own, right. So to calculate the forces or the contact forces when the material come in contact with each other, right. So in the software, basically most of the software has this part. They have a kind of creator, right, then simulator, then analyst. In the creator, like you are talking about, we need to define the properties like coefficient of restitution, coefficient of static friction, right, coefficient of rolling friction. And do you think it should be between particle and geometry alone?
No sir, particle to particle also it is involved.
Okay, particle and particle interaction is also there, all right.
The surface also.
Particle and
Which surface paper?
yeah, surface geometry of the material. So how will you define, how will you find or determine the particle-particle interaction for the, or say the coefficient of restitution for between the particles? Is there any way?
Two particles are there, so like as you told, like velocity before, after collision divided by before.
But the impact is very, say in a mill it is moving very fast, or the impact is at very high speed. How to determine that? Any guess? There are special cameras, right? Slow motion and high speed cameras kind of, right? So they can do frame by frame, and there are other ways of doing so. This is by the calibration test that we will discuss, right? Say particle density is there, we can find it out, right? So coefficient of static friction between the a grain particle and the wall, say stainless steel wall is there, right? So we can easily find it out via some standard methods, right? But the say coefficient of this your friction, right, between the particle and particle, again it is difficult to find, right? So that in that case we need to do some sort of calibration test. So once we put in the properties with a certain contact model, we need to define or import the geometry, our own geometry. Say in this case a screw conveyor is there and material is fed from the top side, right, at certain feed rate of say 2 kg per hour or so, right? And we need to define the rotation, direction of the rotation of this screw, right? At what speed we are expecting it. And for example, I am interested in the discharge rate. So that then there comes the analysis part. So I can put on a bin on the bottom side and find the discharge rate of it, right? Say I can find the mass or the number of particles with certain time, within certain time, so we can get the rate, right? So this slide shows the overall thing, right, in the modeling and simulation part. You need some input parameters that are there. Appropriate physics, that means this is the contact model, we need to define that. On the top you can see the particle shape, like in the earlier lectures it was talked, right, you need to define the particle shape. The shapes are little different, we may get a different result. Of course there are variation in the results, say it can vary from 10 to 40%, depends, right? So if it is a sphere, it is very easy for us to do so, right? So if it is an oval shape, right, so they on the top you can see the shapes are formed by clubbing different materials, different spheres. And then we can also define the particle size distribution. Say my particle size is varying between 9.5 mm to 10.5 mm. So we can define that, right, while feeding also. Now another important criteria is the time step, right, where we also call this as numerical time step, right, in the simulation. So in this numerical time step, right, this is the minimum time which is taken while iterating this, right. So it is defined by the Rayleigh time, right, Rayleigh wave. This wave is the surface wave, right. We can define its speed by this formulae on the right side. If you know the speed, we can find the time also. So this is Rayleigh time, which depends on the diameter, right, coefficient, diameter of the particle or the radius of the particle, density, right, shear modulus, right, Poisson's ratio of the particle. So once this is defined, we can give the time step, and it generally varies between 10 to 40% in the case of food process or food grains, right. So what if I put on the higher side or the lower side of this, right? Let us see this by an example. On the right side, I took in my simulation 10% of TR, right, that is the time step. So you can see a very good behavior of the particle interacting with the conveyor. On the left side, I put it as 50%. Rest of the thing I did very well. Say I put all the input parameters or the coefficients, right. I put it in a nice way, but I failed it here. So I cannot do my simulation. You can see the particles are scattered, right. There is no interaction between them. So this is also a very important thing, right. So like I told, there are different contact models. In this slide you can see force and overlap of the two particles, how they are interacting. Say overlap is higher, it is defined by JKR model, right. It means it is more adhesive. Our sample is more adhesive, then I will select JKR model, which is an inbuilt model, right. And we can develop our own model and we can put it in through API, right, application processing interface. And then there is on the top, there is good greenish color line, you can see Hertz Mendelian model. It is generally for freely flowable particles, right. So we generally select this one once we are interested in free flow of the particle, right. So, this contact model selection or developing our own contact model we can do and put it on through application processing interface, and this is dependent on the applications most of the times, right. Say I am interested in the dry granular material flow, I will select Hertz-Mendelian model, right. And I am if there is a cohesion, I may be interested in JKR. If it is not solving the purpose, I will develop my own model, right, or you can develop your own model. And then heat transfer, it is limited to the conduction part only, conduction, heat transfer between two particles via conduction only, right. If say you are purging some gas, hot gas, blowing it through the blower from on the top of the grain, right, on the top of the grain you are blowing it, right, and for the drying purpose you are using. So, DEM alone cannot do all the job, you need some say CFD part also for the, since this is the fluid which is flowing in a continuous matter and we need a coupling of them, right. Then bonding model, this is right, bonded particle models are there, right, to create a bond between the internal particles. Right. Then if you are interested in electrostatic part, that is also there, so you can do. Now the shape representation that I was talking about earlier, right. In this shape you can see a maize grain on the top, right. And it can be represented by say joining the 5 particles, 7 particles, 11 particles. What do you think, if it is computationally intensive or expensive process to use a larger number of particles?
Time taking only.
It is time taking. So what we can do? It should not affect our final result, right. So accordingly we need to select them, right. And on the bottom you can see a pepper seed, a black pepper seed is there, right. And I was interested in the grinding part, right, and we are taking the bond, I chose the bonded particle model and defined certain stiffness, and I chose certain number of particles based on the force deformation characteristic in the UTM, universal testing machine, right. So here are 522 particles, and again on the back side of that we did a X-ray imaging of that, right. Based on the X-ray imaging we find that there are some percentage of the pores, say for example 20% pores are there, pore space is there in the pepper, and 80% are the solid particles. So based on those 80% of the particles we developed the bonded particle model for the whole grain, right. So it is made up of fully solid, right. Like coefficient of restitution, say we need to find the coefficient of restitution between particle and particle. So we can do this by some sort of geometry, making the geometry via some calibration test. Here we selected a rectangular box, defined all the properties, and the box, on the front of the box it is removable, the plate is removed by putting it, right, and it flows down, right, it passes away. So we need to quantify also, we need to cross verify this, right. So we tested it with the angle of repose finally. Once the grain moves out, we simulated the same condition in the actual in the software, and we find the angle of repose and the height of the seed retaining the wall. So that initially in this test we can say, yeah, if it is matching we will go for the bulk or the larger number of the particles we can go on, right. That means our input parameters, the varying by guessing the parameters, if they are doing well in the simulation we can take them and move forward, right. And in the powder, there a powder rheometer is used by a researcher, and they mass shear this coefficients and all with the their graph, force and deformation characteristics in this simulation as well as in the rheometer, right. So they cross check the results and then they use it for further analysis, right. Now let us see some of the application of DEM simulation in food engineering and technology. Like this, in this example, this is for the grain silos, right, a filling of the grains from the top of the silo, right. Say 100 ton of silo is there, it is filled, right. We are interested in the compaction and other studies that we will see, right. Then there is a stagnant zone, rest phase is there. Now at the time of emptying also, once the bottom pan is removed, right, you can see the discharge pattern of the grains, right. In this we can do different testings, right? How to design the silo, or our silo is correctly designed or not. Like you may be aware of the rat holing in the silo. Rat holing issue? Okay. What it is?
Yeah.
Mass flow and funnel flow? Okay. Pipe flow? Yeah. So say a stagnant zone in rat holing, a stagnant zone is created on the two sides of the silos, right, due to compaction or so, right. And then if you open the bottom of the silo, the top grain will move out first, right, due to piping funnel, right, due to funnel flow. So that is not desirable. So you can go on in the depth of this case, or you can study this, right. So this is, in this you can see how it is taken at the micro zone, or the particles too, right. Then grain sieving process, here you can analyze the throughput of the grain, you can change the sieve without actually designing it, right. And right, you can do it for the other particles also, not only restricted to the wheat, you can take other grains too, right. And this I had taken for the cauliflower grading, right, a cauliflower grader is there, right. The source of this is an Edam community, right. So in this cauliflower grading, what they are doing is they develop their own cauliflowers with binding little particles with in the shape of the cauliflowers, right. And then they see the throughput and optimize the efficiency of the system and the processes. This is just to give you an overview of the overall the things which are happening, right. Then this is the case of the potato grader. To see the damage in the grader, there is a conveyor, it is falling on the bottom of the bin, right. And in some cases, to fix the height of this conveyor, right, it is used. And it is widely used in the grain drying process. You know, in the mixed grain dryer, this for the grains, there is a loss of around 8% of the non-uniform drying. Not a loss, I must say. It is a non-uniform drying of the grain, and some of the grains we cannot eat. So that means there is a loss, right. So in this slide, you can see a hot air is blowing from the center of the chute, right, and on the bottom you can see that it is heated up, right. The temperature is higher. This shows the temperature profile of the grains, right. So we can change the design of this, right, a little bit, or the blow of the air. But again, we need both of the things. Not only DEM, we also need some finite volume method or CFD thing, right, coupled together. Now this is the case of the cryogenic grinding of spices in single slide. I am explaining this. This is my research work overall. I did it for around 4 or 5 years or so, right. On the top you can see a pre-cooler is there, right. It cools down the grain and brings the temperature of the, say I took a pepper spice to a very low temperature, say -80, -100 degrees C, right, before falling this into a grinder, which is on the bottom side, which is a hammer mill, okay. So cryogenic grinding is a low temperature grinding process where we use some sort of cryogen like liquid nitrogen, right. So on the top, from the top of the conveyor, we are feeding the grain, say at a rate of 2 kg per hour, and we are interested, the grains are cooled down and it is falling in the mill, hammer mill, right, and it is then broken down. So this thing is modeled and simulated in DEM, right, via DEM software, right. So on the right you can see we made an acrylic sheet, transparent sheet is there, and we observe the flow of the particle in this screw conveying type of device that we call as pre-cooler, but there is no purging of the liquid nitrogen. We are interested in the moving of the grain as well as the conduction between the contact models, between the two particles, right. You can see with the simulation time on the bottom side you can see within 129 seconds of the simulation or the flow of the particle, it is still at -196 degree or so, right. We assume that the temperature of the particle at the entrance is close to -196, right. Then with the motion, you can see with the geometry, that is the stainless steel geometry, some of the particles are heated up, right. Their temperature is increased. It is around -79 or -50 degrees C, right. So this is with the Hertz-Mendelian model, which is with the heat transfer conduction model, we clubbed together, right, and we provided the parameters. this is how it looks like in the simulation, right? I think it is not playing. Let's see. This, on the top you can see the simulation time, right? 150 second, 200 second. And the grains are entering from the hopper, top of the feed hopper, and it is passing through this conveyor. Right? And you can see the temperature changes within the particles, each particle. And then it is coming from the outlet. And the temperature on the right side you can see for most of the grain it is around minus 70 to minus 80 degrees C and close to minus 50 also, right. So this is just an example. What do you think, what is the actual time which is required for doing such sort of simulation? That depends on the machine, of course.
Computer
Yeah.
which we are using.
For an
Generally, like for 1 second of real time, approx 1 hour.
you have to, yeah, that is right. It took around 1 to 2 hours depending on the system we are using, and you can see only the simulation time which is showing us 325 seconds. Right? So it is most of the time consuming if you do not have a good system, right, with you. You require a very good workstation with you, right, or a high-end computer. Then once enter the mill, right, we, like I told, we developed a bonded particle model for the pepper, right. On the left bottom side you can see the bonds within the pepper seed, right. This is shown by the red and some cyan color, right, and bluish color it is through the vector diagram. Each particle is represented by the vectors, and we are compressing this particle in a universal testing machine, and we observe, you can see within inside the force deformation characteristic of the particle. Right. I selected 500 particle, 1000 particle, binded them together with some properties of the particle, right, the bond properties that we say. Okay. And then once it matches with the force deformation characteristic, we put those properties in the mill, right, and you can see the scattering of the particle, right, within the mill, how the particle breaks down. In actual practice in the mill, you can see it is very within the fraction of seconds the particle will be broken down, but we cannot see even with the camera, right. Even with a high speed camera we cannot see. Particularly in the case of cryogrinding, if you put on an acrylic sheet, there will be a gaseous nitrogen also there. Again, it is blocking your gaze, right. So then how to validate this? We did with some sort of quantified qualitative analysis as well, and quantitative analysis of the particle as well at the outlet of it, right. Again. Okay, so this is the bonded particle model which we developed for a single grain. Then you can see how I took 50 particles. Each particle is having around 500 particles. 50 into 500 you can calculate, right, and with the bond properties and the Hertz-Mendelian model, right. So you can see the particles which are broken down on the bottom side of it is there is a sieve, right. So it took around 73 days to me to do just this job. So it is really time consuming. That depends again on the machine, right. So this is the qualitative test, right. There is a feeder on the top, right. We removed the feeder, and you can see the sticking of the particle there, and it is similarly true in the case of your simulation results, right. And then we took those particles and measured the weight, and we can't measure these numbers, so we did it by the weight and cross verified it with the number of the particles, right. And based on this breakage study, right, we find that within this simulation time of 5 minutes, right, initial 0.2 seconds are the particle we assume as the whole particle, and after that some reduction in the size, then again the reduction in the size, okay, and we measure the temperatures of it, right. And there is a variation of around 25 to 40%, right, between the simulated result and the actual results. And the temperature is measured by placing the thermocouples on the three sides of the mill, right, left, top, bottom. Right. So, what more we can do, right? This DEM can be coupled with FEA, finite element analysis, right? FEA. In FEA, you can get the structural analysis, right? While DEM will do the part of this discrete particles and all, and they can be coupled with each other, and you can see the realistic behavior of the particle in a, say, a conveyor or a hopper there. Then it can be coupled with DEM and CFD, right? Like this is a grain dryer. The grains are there, which is taken care by the particles, right? And the hot air is blowing, so you need a CFD part too. But we can interplay with this, right? We can change this. It can be used in the drying, fluidized bed drying, mixing, right? And others and similar applications we can say, right? So in summary, we can say we can predict the bulk behavior of the grain by modeling each and every single particles with DEM, right? Any questions? Okay. If you are interested in this topic, I had written a book chapter, and you can go on reading this, right?
Check.
If you have a question, I am very happy to take it. I cannot cover this in the 1 hour class, but it needs much time. Okay? Yeah.
Sir, while doing the simulation, is there any need to calculate time step?
Yeah, you can cross check the time step. Okay.
Cross.
There is a formula for calculating. There is a real time step. You know the formula. You know the properties, right? If you are you find the real time step as, say, 1 second. And like we told, for most of the cases we take in between 20 or 20 to 40% or so. You can put it on in the simulation, right? That time step that you got, right? It will automatically calculate in the software actually.
Yes.
But if you want to find it by yourself, you can do that.
Yes.
If it doesn't work, you need to take a lower time step, right? Iteration time. It is mostly true in the case of the very high speed particles.
Yes.
Right. Yeah.
And my another question is like you taught us a methodology, rectangular box.
Yeah, that one. Yeah.
So it is necessary before simulation?
No, it is not necessary at all.
Yes.
Right? Since there are not the standard methods for in the case of the food grain, there are variety of the food grains,
Yes.
So it can depend. And there also we need to consider the wall effect between the grain and the wall. Right?
Yes.
So for designing that, you need to consider other aspects too.
Okay. Thank you, sir.
Okay, thank you. Any other? Yeah, Dr. Singh.
Hello, sir. What are the
Yeah.
what are the application in pharmaceutical purposes?
In the pharmaceutical purposes, you are asking?
Yeah, for the capsule and all.
For a capsule and all,
Microencapsulation,
right.
yeah.
Right. When you make capsule, capsule filling machine is there, right? And you are mixing some drugs in the capsule, right? And if you want to see really a capsule is made with it or not, right? And the interaction of the particle. So this can be done since this is the case of the powder, and you can make a capsule, right? Even you can see the interaction of the capsule with the packaging material, the mechanical behavior, right? While the transportation also. Yes. Since I didn't work in this same area, but just you can go on in this case. I was expecting something else from you. You talked about earlier we interacted with in the case of the fruits, right? Fruit and vegetable transportation. Yeah. Anyways, is it fine? Yeah.
It's fine.
Okay. Thank you. Any other question? No? Okay. Then we can interact and take around of the department, right? Thank you. Okay. Keep the doors open, right? Who is having the key? Okay. दरवाजा खुला रहेगा.